For this presentation, I would like you to imagine that you're the owner of an EV or an electric vehicle, even if you aren't. And right now, on the current market, your EV can drive about 200 to 400 miles per charge. So in not American words, about 320 to 640 kilometers per charge. But there's a new EV on the market, and it can now do 1,600 kilometers per charge. And I would like you all to think how much more you'd be willing to pay for that kind of mileage with one charge. So that kind of car probably has what we call lithium sulfur batteries, which is what I'm going to be covering in my presentation today. All right, now we're going to start with the background and what's the current technology that's on the market for your electric vehicle. So right now, as we all know, our energy storage demands keep on increasing, right? So we have artificial intelligence. Every day our technology gets bigger and better. And what does that mean? We need more storage. We need more energy to fund that kind of technology that we're making. And the major two contributors to our increased energy demands, number one, EVs. So electric vehicles are becoming increasingly more common, right? And also grid storage. So if you've ever heard maybe an engineer say, we'll save it to the grid, essentially what that means is we're saving excess energy for later use. So as we have more technology that requires energy, we want to be prepared for those emergency situations where we need a burst of energy at once, say in a natural disaster. So that grid storage is also increasing that energy storage demand. So, however, in your current EV, your hypothetical EV, you probably have a lithium-ion battery. So that is the current generation of batteries. That is a big version would be in your EV, but also smaller versions in your phones, in your computers, normal technology like that. Now, lithium-ion is great for today, but we want to be prepared for the future. Right now, it's able to perform well enough, but we also have safety concerns as well, which I will talk about later. It's also quite costly. So lithium itself is moderately expensive, but there's also kind of these rare metals that come with those batteries. Those rare metals are quite expensive. So we're talking cobalt and nickel. Not only is it expensive for your pocket, but it's also expensive for the environment. So to get those metals, we need to mine deep within the earth, which can really hurt our environment. So which is why we need to change and make a pivot for the future. Now, I want to go more into what I was talking about with this increase in energy storage, just to really illustrate how fast it's coming. So where we are right now, 2025, that's going to be your middle arrow right there. So you can see that it's pretty high, about 75 gigawatts, right, just for energy storage. And our main kind of like contributors are, number one, that red bar, as you can see, is taking the majority. That's going to be China, followed by the US. So those are our main countries that are kind of taking a lot of that energy storage. Now, I want to look back to 5 years ago, 2020, the year of the pandemic. It doesn't feel that long ago, but look how small that energy storage capacity is. I mean, compared to what we are now. So it's only been 5 years, right? But look how much our energy storage capacity has changed. And you don't have to be, from an electrical background or an engineer background to see that that seems like it's not sustainable. Right, and we're also going to look at our projections. So based on our data and just on technology, we've used algorithms to project what kind of energy are going to need 5 years in the future, in 2030. So that over there is already topping 100 gigawatts. Looks like China and US are also going to be major contributors to that, but you can see that clearly something needs to change. Either we use less energy or we have more efficient ways to provide that energy. So your hypothetical EV probably falls within one of these models, right? So these are our most common electric vehicle models. So at the top is the Tesla Model Y. The Tesla Model Y is very common in the US and China, which goes back to what I was saying with the US and China really contributing to that high energy storage demand. Then there's also quite a few BYD models, which are more common in China. And all of these models are going to be your really common electric vehicles you see. And based on economics, we are going to see probably more of those models coming in the future. However, here's a YouTube video that we're going to see a lot, right? So on the flip side, people are saying, how safe are they? So say you're driving your EV, right, your hypothetical EV, and you listen on the news there's a story about a Tesla battery exploding or a BYD battery exploding. That is going to be quite scary to you if you're driving an EV or you're considering to drive an EV. It may be enough for you to not to trade in your EV, go for gas, or just not get an EV at all, right? Because even a slight risk of it exploding is enough to cause great concern to you, which is why we need to pivot to a more safer alternative. So now we're going to say why lithium sulfur. So this is the next generation battery that's going to power that 1600 kilometer per charge EV. So it has a very high theoretical as well as practical energy density, about 2600 watt hours per kilogram. So comparing that to what we have right now, the lithium ion is only about 150 to 300 watt hours per kilograms. So as you can see, that energy density is just shockingly much more significant. Now, another great thing is that we're using sulfur, right? Now, sulfur is going to be as a result of volcanic activity as well as petroleum mining. It's a lot more abundant. Now, that's good because one, it's going to cost less to make these batteries, and it's going to be better for the environment. We're not going to have to drill deep into the earth to find sulfur because it's much more abundant. Now, everybody's saying, wow, this battery performs better, it's cheaper, and it's better for the environment. There has to be a con, right? Now, the challenges with this one are just that it's so futuristic. We're still on research R&D for that, which is what my research is tackling with that. We're also having this effect called the Shodel effect. So I can see here on this diagram on the left, we have lithium in that green and then sulfur in that yellow. You also see in the middle, there are some kind of molecules there. So when we charge the lithium sulfur battery, we have these things called polysulfides come up. And that's what us researchers are really trying to tackle. So these polysulfides, what happens is when you charge and discharge that battery over and over again, right? So you want to charge your car multiple times, not just once, maybe hundreds of times. Those polysulfides are going to get kind of stuck. And every time you charge that battery, it's going to require more energy, slightly more energy to do it the next time. What that happens is that your battery deteriorates more, so the lifespan is less. And now we're gonna look at side by side how that lithium sulfur battery is gonna be better. So like I talked before, lithium sulfur has a significantly higher energy density, right? So the lithium ion, just as a reminder, is what you have probably in your current EV, but the lithium sulfur is significantly higher energy density, meaning it's going to be able to contribute more miles per charge. It's cheaper than a lithium ion due to that abundance of sulfur, right? Because the lithium ion currently uses cobalt and nickel, which are harder to find. Then you also don't have that flammable electrolyte risk. That's a major plus, especially for selling it commercially. So when we're talking about R&D, we also have to talk about the commercial sides of things. What is going to happen when you put this on the market? The main thing that people are most concerned about is going to be safety and performance, right? So we have a great performance and we have a great safety, right? And I'll go more into why that flammable electrolyte is a risk later, but lithium sulfur is also more environmentally friendly. So that's going to appease, more of like the legislative side as well, since we're much more concerned about the environment as we're going in, because that should be concerned to all of us. However, more research and development needs to be made to make this commercially available. We already know that it's a great solution, but we need to take that research and take that step forward to put it on the market so that you can have a great EV and a safer EV as well. So now we have the solid state lithium sulfur batteries. This is the next generation and what I focused my research on. So we are replacing a liquid electrolyte with a solid state electrolyte. Now the reason why batteries explode is because a lot of times you have very hot temperatures in a car. So when you're running a car, obviously within the interior of that car, it gets to extremely high temperatures. When you have a liquid, what happens is that it can learn to thermal runaway. So the temperatures within that battery are so high that it damages the battery. And what's really scary is that the liquid electrolyte can leak, right? So when you have that liquid electrolyte, it can leak in places that you don't want liquid to be, and especially very hot liquid can lead to the explosion of that car. But with a solid state lithium sulfur battery, you're using all solid materials, so you don't have to worry about that leakage in your car. You don't have to worry about that flammable electrolyte. So you have improved safety and improved stability. However, with that reduced with that reduced transport, right, with that reduced flow, you also have more sluggish ion transport, which is what my research is trying to overcome. So although it's more safe, we also need to make sure it's effective as well, so we can really harness that potential that comes with the really powerful energy density with the lithium sulfur batteries. Okay, I would like to go back to the shuttle effect that I talked about earlier. So within the solid state lithium sulfur battery, we are going to have a little bit of that shuttle effect. So we are going to have some leftover polysulfides, but with the solid state, we're going to have less. So we're going to have as well some oxides, some polymers, and those are going to be less harmful and lead to a longer lifespan for that solid state lithium sulfur battery. Now we're going to go into what my research is going on about. And I will say I'm currently not finished with the research. I'm currently in that experimental stage, but I'm going to talk about what we're doing right now and also how I'm going to extend that research. So this is a research objective. So to analyze chemical and structural changes during operation using operando Raman spectroscopy to identify sulfur species and evaluate degradation mechanisms. Now that was a lot of technical terms, but I'm going to break it down if you don't know what Raman spectroscopy is, because I did not know before entering this research. So essentially on the side you can see a really general overview. So I'm going to make my own solid state lithium sulfur battery. Then I'm going to test it using this spectroscopy method, analyze what's happening on that molecular level. Because once we understand what's happening on that molecular level, we can understand what we can do on the macroscopic level to help make these batteries better. That will lead to insight and lead to better design, so we can take this amazing battery and make it into a commercial alternative. All right, so what is Raman spectroscopy, right? So Raman spectroscopy is a type of light scattering technique. So when you shine a light on something, specific energies of light on a specific compound, it will reflect that light. Now, based on the compound, what happens is when you scatter light on something, the molecules will vibrate in a certain way. When those vibrations occur, it'll scatter light in a different frequency. Now, that is what we measure. So based on the identity of that compound, it'll scatter light in a different way. We take that frequency and we're able to understand what is the physical structure of that compound. So we're detecting those molecular vibrations, and it's ideal for monitoring, okay, we have these compounds that are coming up, what is the structure of those, right? So we look at our data, which is the light, and then we analyze the compounds based on that Raman spectroscopy. And the great thing about this method is that it's real-time monitoring, right? So we don't want to just know what's the start product, what's the end product. We want to know every single molecule that's coming in that, so we can make this battery even more efficient. So here is the experimental setup. So we have a sulfur cathode with a lithium metal anode, right? So that is our lithium sulfur battery. We're also using a P.PSS polymer electrolyte. So think of the electrolyte as where the ion transport is happening. I would say this is where usually the danger with liquid electrolytes come in, because this is usually the liquid component that usually explodes. So with this one, we're using a polymer, which is a solid material, but it's also quite flexible. So we're kind of going in between that liquid and solid to still be safe, but also be effective. And we're using operando Raman during cycling to understand what is happening at every stage. On the left is kind of a predicted Raman spectroscopy that we're expecting to see, but of course, we will also compare that to the results once we finish that as well. So here is kind of the physical diagram of what's happening. So we're going to have the battery that's going to be constructed, and there's going to be a Raman probe that's going to show light, as you can see on that battery. The scattering beams is going to be our data, or our dependent variable, and we are going to analyze that to see what is happening on the molecular level within that battery. So putting this in literature, we want to compare it to what's happening with the liquid state, solid state, the liquid state lithium sulfur battery. So that reaction pathway I have, I'm not going to read it out, but those are basically the molecular stages that is happening in the liquid state lithium sulfur battery. So we know that that's happening in the liquid state, but we don't know for sure what's happening in the solid state, which is what my research is doing with that Raman spectroscopy. And we are less understood about the solid state systems, one, because they are harder and to make, and they're also so next generation. Now, the reason why we're thinking that far ahead in the future, not just lithium sulfur batteries, but solid state lithium sulfur batteries, is because we need to be in a position as a society to tackle that increasingly rapid energy storage demands. So we need to not just thinking, what about tomorrow? We need to think a year or 10 years in the future. So that is why we're looking at the solid state lithium sulfur battery, and why we're going to understand we need to know what's happening on the molecular level so we can engineer a battery that is more commercially available. So here are anticipated results. So I anticipate the sulfur species S8 and Li2S2, and there's going to be a sulfur conversion, but not a complete sulfur conversion due to the more sluggish ion transport. Now, with that information will be significantly important because it'll allow us to adjust the battery design so that the ion transport is expedited, and it'll lead to having all of that energy density that I was talking about earlier. And that is going to help us design a battery that is actually commercially available, that can actually have that theoretical energy density. Because while for scientists having that amazing theoretical energy density is great, it is not impactful to wider society until we can get it into a car, into an EV, right? And this method is valid because it has been used for our regular lithium-ion batteries, but just hasn't been used for those next generation batteries. Going on for that, we're also going to go to impedance spectroscopy. Impedance spectroscopy is basically just a technique in which we analyze how well the electricity is flowing. So once we know what's happening on that molecular level, we're going to understand how well is the battery running. And we're going to evaluate how well is that energy density. Right, and now we're going to go on to analysis. So I was talking earlier about that electrolyte. Now, when I'm going to expand my research, taking this a step further, once I finish this research, I'm going to understand what is the best electrolyte. So that's the next step. What are the best components of this? So on the left, you can see kind of this more like patchworky material. That's a polymer electrolyte, like on the very molecular microstructure. On the right, you can see a ceramic electrolyte. So if you just think of your regular like ceramics, that can give you an idea. So a ceramic is a very hard material. And on one hand, it's good because it's more conductive, but it's also very brittle, right? So if you have a ceramic dish, it can break very easily. On the other hand, you have a polymer. So it's more safer, it looks more flexible, but it has lower conductivity. So as a lot of electrical engineers like to say, with every single material, there are pros and there are cons, and we need to weigh those and have a risk-benefit analysis to understand what we need for our specific battery. And I am considering hybrid designs, right? Try to use the best of both worlds and see if we can have that conductivity with the ceramics, but also, have that more flexible, safer option with the electrolytes. And that's why I chose that P.PSS polymer electrolyte, because it was much more flexible and has a great potential for having that really nice ion transport that we want in a battery. And here's that hybrid gel electrolyte design in a physical representation. So you can have a matrix, and you're also going to have conductive pathways. Of course, this is going to be on the micro level, so this is not something that we'll see visually with our eyes, but that's what's going to be on the micro level. And for the recommendations for engineers to get this on the market, you're going to need an optimized electron transport, as well as pairing spectroscopy with impedance data. So in other words, what that means is we need to know what's happening, and we need to know how well it's happening, right? So we need to know that how electrons are flowing, but also how well are these batteries performing in the actual discharge of them. So limitations of my research, obviously the Raman's not yet executed, right? And then also there's future, we need to say how long the lifespan is. So for example, the first time you get a phone, it charges really well, but you want to know 2 years, will it be the same? Will it be at 80% capacity, or will it be at 50% capacity? That is something that you would really want to know going into getting a phone or an EV, which is much more important in your daily life. So here are some key experimental stages through fall 2025. We're going to go with cell fabrication, which has already been mostly completed, going on to electrochemical testing, the Raman analysis, and electrolyte optimization. So I would like to end with the broader impact. So like I said, we were imagining that you had an EV, right? So this is all the research that has to go into making your EV go to that 1600 per charge. And it seems almost amazing to think that you can have more energy, but it's also safer and it's better for the environment. So that is almost, it seems too good to be true. And the only thing that we have to do as scientists and as society is to make that research go the extra step so that we can have you have a better experience with your EV and as well as a safer experience. Okay, I'd like to thank you all for listening, and I'm open for questions now.
Yeah, thank you so much, Riya. That was so interesting
Thank
and so
you.
well presented. I just want to ask you, I mean, you mentioned this is quite sort of futuristic work and you're still in the beginning stages of research, which must be so exciting to be a part of. What are your kind of predictions for when we actually will be able to drive these cars and think of you as we drive them? And what do you think maybe the main challenges are to get there?
So I think that the biggest obstacle with these things is the safety. So the fact that we've already proved that it's safe really expedites that for us. So I think the biggest issue when we're thinking like before lithium-ion batteries were kind of on the market, the major thing that slowed that coming on the market was the safety issues. So the fact that this one is proven to be safer makes us a lot more hopeful for when it's going to be. I think that hopefully by 2030 would be great. I mean, I think there's a lot of research, and even while I'm researching, I see lots of other scientists doing this as well. Not just because like research is going to happen, but we really need it. And I think once the energy storage problem becomes really apparent, much more scientists are going to start researching this battery. So yeah,
Exciting.
yeah.
Thank you. Okay, any more
Thank
questions?
you.
No? Okay, so another round of applause. Thank you.
Thank you.